Welcome everybody to the Csig talk series. Typically happens on Thursdays at 10:30 a.m. US Eastern. The topics are AI related, and the recording and slides. The slides have already been posted. The recording will be posted, and I've put the link in the chat. I'd like to welcome today Vijay Arya and Amit Durandar from IBM Research, and they're going to present AI Explainability 360 Toolkit. So over to you, Vijay and Amit, and I am recording.
Thank you, Susan. Hi, everyone. I welcome you all to this, this talk on AI Explainability 360 Toolkit. So in this presentation, myself and Amit will just cover sort of a broad overview of the toolkit we've just released. And then we open it up for questions at the end of the call. So Amit, can we go to the next slide? Thanks. So I guess one of the reasons, one of the changes that we've seen in the last couple of years is the fact that AI has started moving from lab kind of environment to several real life applications. So it's possible when you sort of apply for a home loan. Your application could be scanned by an AI model, or let's say if you're trying to apply to a university or one of the companies you want to work in, and it's possible that your resume could be scanned by AI. And similarly, for sentencing and for healthcare and a lot of other applications, AI has started impacting our lives. So accuracy alone cannot be the only metric that that we're going to use for measuring AI models. These models need to sort of satisfy several other criteria. For instance, the decisions made by AI models need to be fair. They need to be transparent or explainable, and they need to be secure or tamper-proof, and also they need to be accountable, so that we can trust the AI models and then rely on the decisions made by these models. So let's go to the next slide. So, so what we have done in this particular work is essentially released an open source toolkit called as AIX360. Now, the toolkit actually has 8 different algorithms to explain data, machine learning models, and their predictions. And along with the toolkit, we also have an interactive experience which is more accessible to data scientists and practitioners. And Amit will be going through part of that demo in this talk. We also have an API along with the toolkit. And the good thing is that we have about 13 notebooks, and these notebooks give examples of how you could use the different algorithms to explain models, their predictions. Take a look at data. Figure out different types of insights from the data and so on. And overall, we had about 15 or so developers and several software engineers, and all of us worked together to come up with this toolkit. So this toolkit actually is in is part of a series of toolkits that IBM Research has released. Last year, we released the AI Robustness as well as the AI Fairness Toolkit. And so this year, we are releasing the AI Explainability Toolkit. And we also have a couple of other toolkits lined up under the Trusted AI umbrella. And the goal of these toolkits is essentially to support a community of users who would help make models more transparent, and also engender trust in AI. And the other goal, of course, is to support the growing research on explainability, so that researchers could use the algorithms, compare different algorithms in the toolkit. So let's move to the next slide. So one of the unique things about explanations, as I mentioned in the last slide, we have about 8 different ways to explain machine learning models. So this is because explainability actually, different types of users require different types of explanations. So one type of explanation may not meet the requirements of all the different stakeholders who are typically involved in the AI value chain. For instance, take a look at an end customer. An end customer, who could be like let's say a home loan applicant, or a doctor or a patient. and they want to know, why did the AI model make a certain recommendation for typically for specific instances of the data points. For instance, there could be a patient, and he may want to know why he has been classified in a certain manner by a healthcare model. So these are one type of explanations which are typically, required by end customers. So these are typically called as local explanations, as Amit will cover later. Now, another type of explanation is typically required by folks who are developers and also regulators. Now, these type of folks typically require an overall understanding of the model. Why is the model making certain types of decisions overall? And so that, they can actually debug the model. They can figure out, if the rules that have been learned by the machine learning models are indeed the rules that they had intended when they actually eyeballed the data in the beginning. So these type of explanations are typically required by debuggers, and also for regulators if you want sort of audit your model by a third party and so on. And here we typically have global explanations. So these are just a glimpse of two types of explanations that I've shown in this slide, but there are actually a wide variety of explanations which are required by different stakeholders, which is going to be covered by Amit. And that is one of the reasons why we have 8 different algorithms, and also there are actually multiple other algorithms in the open source literature that we plan to integrate over the in the future in the toolkit. So over to you, Amit.
So thanks, Vijay, and thanks everyone for joining. Yeah, so as Vijay was saying, there are different ways of explaining depending on who the users are or the consumers are of an explanation, and essentially who are essentially the action entities. So given various ways of explaining, we have created this taxonomy, which we hope that helps people essentially navigate this space of explanations and interpretability in a more sort of intuitive way. So what we have in this taxonomy is that at the top of the taxonomy, as you can see, we have 2 branches, one for static and the other is interactive. So what we mean by interactive explanations is essentially if you can go back and forth. The current version of the toolkit has mostly, as you can see, static explanations, and so the question mark indicates that contributions for interactive sort of explanations would be highly sought after. One of the things is also that a lot of the explainability research, since it's kind of nascent in some sense, has focused mostly on the static case, where essentially you have these one-shot explanations. So there's very little sort of there's hardly a notion of sort of going back and forth and sort of incrementally building on top of a given explanation. But nonetheless, even under the static branch, you can either try to explain data or you can try to explain a model. So although most of the work has been on the AI model space, the data space is also interesting. And under data, we have essentially 2 algorithms which can explain data sets in terms of either summarizing them compactly in terms of a few samples. So for example, if you have like a digits data set, say like MNIST, it's impossible for if you didn't know it had like 10 digits, it's impossible for a person to look at all the 50,000 whatever entries. But a method like Protodash essentially would select a few of those representative ones, so maybe like 10 entries, and give you a sample of each of the digits, so that a person would quickly have an idea of what this data set might contain. There are also other things where you can also explain in terms of higher level features. So for example, like in image data sets, like individual pixels are not really interpretable. But as humans, what is interpretable is, say, for example, if it's images of people's faces, things like, say, if a person has a mustache, or complexion or pose of the face, and so on and so forth. So there are ways of extracting these higher level features, just given essentially image data at pixel level. And so we have a method currently in the toolkit which can essentially do that. On the right side, which is, like I said, the more busy side, or the place where most of the focus of explainability is on explaining AI models. Amongst AI models, you can have essentially two ways of explaining. So like Vijay was saying, if you are a patient, you might care only for, say, if you're a patient and you have a diagnosis, you might care only about your specific case in terms of why were you given a certain recommended treatment and so on and so forth. So this is what we term as local, because it is very local to that specific individual. But you also could want a global overview of what's happening. So that would be appropriate for regulators, where you want a global understanding of the model and not just independent sort of local explanations. So you can have local and global. Then under global, you can have essentially a model that's already directly explainable. So let's say, for example, like you can just build like a small decision tree. So currently what we have is two rule-based methods, which will essentially create very intuitive rules for you to understand as well as predict what is happening. The other option is that you already have a complicated model that has been built, and you want to somehow explain what's happening in that complicated model. And so here we have one option where you can actually build surrogate models with high performance. So say, for example, if your original model is, say, a neural network, you may be able to transfer successfully to, say, a tree, or even the rule-based models and so on and so forth. So under the visualized category, again, we currently don't have anything. So contributions there are welcome. Under the local category, again, you can have something that's more post hoc and the other that's more direct. So the direct method, like, so the current thing that we have, we call TED, essentially can generate predictions as well as explanations if the data set is essentially enriched with user specific explanations. So for example, if it's like a loan application, and the loan officer might put certain sort of comments when approving or rejecting certain loans. So if we have that information, the model can actually create not only sort of predict or not only try to estimate if someone's loan should be accepted or rejected, but also recreate the explanation that might be appropriate for it. Here also you can do this. So here also you have post hoc methods where you might have some complicated model, and so you may not be able to understand what's happening in general, but you might be able to essentially extract explanations that are at a per instance or local level, like the patient level. And the current things that we have in the toolkit, again, we can explain based on similar samples. So in your training set, that is, if you're a patient, maybe similar patients or patients who had sort of similar medical history as yours and who are recommended essentially the same treatment, so that you get more confidence in what the recommendation is. Or again, here also you can have feature-based explanations saying that, oh, because your sugar levels were too high, you were diagnosed with diabetes, or because you had a family history of diabetes, and so on and so forth. So we have these sort of feature-based methods, and in fact, one of the interesting things of the feature-based methods is that it's also gives you what would have changed the decision. So these are currently the 8 sort of algorithms that we have. There are also 2 metrics, quantitative metrics, which essentially try to act as proxies for measuring how accurate some of these explanations are. So those are also available through the toolkit. So this is a quick comparison of so the top row is our toolkit, and these are some other toolkits that are available in the open source. So we can come back here if someone has any questions, but basically, as far as we know, ours is the most comprehensive toolkit that's out there for explainability. Also, one of the nice things is that most of the other toolkits have a mixture of algorithms from different places, but even though ours is typically more comprehensive than the others, all the algorithms are from IBM research. So that's one of the nicer things. So now what I'll do is I'll just show you a quick, I'll take you through a quick demo of a specific use case, and then I'll hand over to Vijay to take you through tutorials which are specific to that use case so that you get a feel for more of the details. Okay. 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 So this is so AIX360.mybluemix.net is the URL, and if you go here, we have a web page which will essentially give you guidance in terms of how you could use and leverage the toolkit. So we have demos, resources, events, and community, plus all these links which will essentially give you more information. I'll just quickly jump to the demo. So the demo that we have is for a specific use case which is related to the FICO dataset, which was released last year, where FICO ran an explainability challenge. And actually, one of the algorithms that's part of the toolkit is the one which won the explainability challenge. So that's part of this toolkit. And the goal of the FICO explainability challenge was that given a home equity line of credit data set, where each sort of instance was information about an individual and his essentially his previous sort of financial and other kinds of behaviors, if one should actually approve or deny the credit. So what I'll do is I'll go through some of the methods and how these methods essentially serve different personas or are appropriate for different kinds of individuals, and which is one of the key aspects of this toolkit, is the sort of diverse users that it can be useful for. So one person that might be interested is a data scientist or a head data scientist who wants to, say, deploy a model, and what he would be interested in is more in understanding the model globally. And so what we have here is that essentially we have the rule-based methods where they will essentially build a globally interpretable model, and you will essentially see rules of this form saying, so external risk estimate was one of the sort of input factors. So it's a score which goes into deciding if someone's loan should be accepted or rejected. And so you can essentially, with this globally interpretable model, you can get rules of this form saying that at what values, what decisions will happen, and how much does, say, increasing this value affect someone's loan being denied or accepted. So you can get a global picture of what's really happening in the model. And this might be useful, like I said, for data scientists or some sort of higher level executives to get a global feel. If you're a loan officer, you might be interested in more local decisions. So say, for example, if a model predicts that the person's loan should be approved, you might want more confidence into why the person's loan should be approved. And so we have a method which will essentially tell you other people who are very similar to the person in question and whose loans were approved. And what it shows basically with this highlighting is that also essentially features that were used in the decision that are exactly the same as the person that you're interested in. So in this case, Alice. And it also gives you a feel for how close a certain person is. So for example, here it's saying that you're interested in Alice, but amongst these three people who are close to Alice, Mia is the closest. And all of these three people paid their loan, and a bunch of the features or factors are similar between Alice and these people. So it will create an explanation in terms of examples. But say if you're a bank customer, you might want a different kind of explanation where, especially if your loan is denied, you might want to know why it was denied, and more importantly, what you could do to essentially change the decision maybe in the future. So we have a method which will do that. So what it will tell you is, for example, for Jason, whose loan was denied, it will tell you what are the minimal sort of changes to his application he could do or improve, say, for example, like increasing credit score and so on and so forth. In this case, it's these three things. So if you have these three things, if rather than their original values, if they were these new values, what the explanation method is saying is that Jason's loan would have been accepted rather than being denied. So some of these factors may be actionable. And it's also possible to focus only on actionable factors. But the point is that the method will automatically determine among the set of allowed factors which are the most important and what is the least change to the least number of factors required to essentially change someone's status. So with this, I think I'll hand over again to Vijay, who will take you through some of the notebooks related to this demo, and also maybe give you a brief sort of browse of the GitHub.
So while the handover is happening, I'll just read one of the questions. Beyond exploring the actual ML rules used, what about how, by whom, and based on what were these rules? How were they derived?
Right. So these rules were the ones that I showed were derived in a completely data-driven fashion. So for example, in the loan data set, you had these various factors like number of satisfactory trades and external risk estimate scores and so on and so forth. So what the rules do is, given all this information and given historical data of people's sort of loans being accepted and denied, it will essentially try to figure out simple rules that are highly accurate in reproducing those predictions. So it's done in a totally automated fashion, based on the input features and the labels, which in this case is loans being denied or accepted. So that's how.
Thank you.
Thanks, Amit. So I'll just now sort of go over the repo and show also one of the use cases as it is implemented in the code in the repo. So this is the link to our repo, github.com IBM AIX360. So if you go here, you can also take a look at the interactive demo that Amit showed. So that information is available here. And if you would like to sort of install the library using PyPy, you can take a look at a link here, and you can take a look at the API through the docs link. And we have some information about the papers of different algorithms which are there in the toolkit. And if you'd like to sort of download the source code and install, and we have a set of instructions here as well. So all of the resources that are related to the toolkit are accessible through the GitHub repo. So a lot of the code is there under AIX360, all the algorithms that have been implemented. But in this call, I'll just go through one of the examples, essentially an equivalent of, the code equivalent of what Amit was showing in the interactive experience. So the examples folder has a bunch of tutorials. This is a 5-code challenge tutorial that Amit went through, but we also have a couple of other tutorials. Each of these tutorials actually explains a certain business case and how different algorithms can be used to explain the machine learning model for different personas. So, and we also have a couple of examples for each of the different methods. So let me just open this particular tutorial, the 5-code tutorial that Amit showed. So as Amit was mentioning, the goal of this tutorial is sort of, the AI model. The goal of the AI model is essentially to figure out if you want to, give the loan to a customer and essentially classify customers as good and bad. And so the data actually has a number of parameters that you can use to make this classification. And it's a labeled data set. So you have the final parameter that you want to estimate, which is the risk performance as, good or bad. But there are a number of inputs that you can take into account, things like what is the external risk estimate, which is the overall score in that particular country, number of satisfactory trades that the customer has made, in the sense the number of satisfactory repayments that the customer may have made, and so on. So if you build an AI model using this data and use that model to decide, for example, if you want to classify a customer as that the loan is approved or rejected, then you may want to give an explanation to the customer. So I'll just go over that particular use case. So when you want to explain to the customer, you want to tell him, okay, why his loan was, let's say, if his loan was rejected, why was the loan rejected, right? Which is an important sort of, question that you want to answer, commonly asked by a customer. Now, another question the customer would want to also ask is, what changes can he make in his application so that his loan will actually be accepted. Now here is where, contrastive explanations can help. So the explanation actually has two parts, as Amit was mentioning. One is a pertinent positive and the other is pertinent negative. And the pertinent negative essentially helps us to figure out, what are the set of parameters the customer can change for his loan to be accepted. So here in the code, we are firstly, loading the HELOC dataset. This is the dataset from FICO. And then, this is typically the kind of, parameters that we have. Here I've just shown like, about 10 to 15 users. And this is just some, data analysis on the data set. But here we start processing the data set. And then one of the things that we need to do when you want to run contrastive explanation method is normalize the data set in a certain range from -0.5 to +0.5. And so this is needed by the algorithm. And then here we kind of train a simple two-layer neural network model. And one of the things that you need to do when you use contrastive explanation method is that you don't need to use a softmax function at the end. The output should still be logits. So that's what we have done here. We have not used any softmax function in this particular neural network. And then here we simply train the network. It's a simple two-layer network. And, we had, train accuracy of 73% and, test accuracy about 72%. And now, let's say you use this model to sort of, make decisions. And so here we're computing the contrastive explanation for one of the applicants. This is applicant number 1272. And so the first step that we do is we essentially wrap the model that we have trained in a sort of framework independent class hierarchy, and then kind of, instantiate the explainer here by, passing in the model. So this is a white box explainable technique. So you need to pass the whole model when you need to explain individual predictions. And here we're essentially calling the explainer to sort of, give us the explanation, the pertinent negative and so on. And it has a bunch of parameters. You don't need to bother about them in the very beginning. You can use default parameters to get the explanation. So we're passing kind of the input instance we want to explain. And here the algorithm is computing the explanation. So once you sort of obtain the pertinent negative, you can see this is how it looks. So this was the original data instance, the customer whose loan was rejected. And what the explanation is saying is, if you increase the risk estimate, the external from 65 to 76, and let's say the number of satisfactory traits from 17 to 20, the loan is going to be accepted. So this information is now available to the customer, so he can see how his loan can be he can sort of apply for loan again in the future. Now another simple question is is a pertinent positive, which you could ask, what is the minimal set of values? His loan was accepted, but can he reduce his external risk estimate a little bit and the loan would still be accepted? So that information can be obtained through the pertinent positive. So here is an example there again. So here, for example, the external risk estimate was 82, but the algorithm says that even if this was about 37, the loan would still be accepted. So these kind of explanations are available through contrastive explanation method. And I invite you to sort of go through this tutorial. The code is very easy to sort of read and understand. So let me stop here. Sorry, I took a little bit longer, and if there are any questions, we'll be happy to answer.
That was great, Vijay and Amit. There are a couple of follow-up sort of comment questions from the earlier question. One is saying the rules were derived on historical data only. It's kind of a question.
Right. So based on whatever training data was given, the rules were essentially automatically learned based on the input and the output. So it's essentially a standard sort of learning scenario where you have a data set and you have the outcomes as well as the inputs.
Mm-hmm. And there's a sort of follow-on remark, derivation of the rules is part of explaining the results of applying the ML model.
Right. So yes. So the nice thing about the directly interpretable rules thing is that it creates a model which is essentially a classifier that will give you the predictions, but it itself, since it's in the form of rules, is interpretable in many cases. So for example, the thing that Vijay showed is after the fact. So he trained a neural network model, which is not interpretable. And so the method that he showed is not going to actually do predictions for you. It is only going to explain at a per instance level predictions of some other model. So with the rule-based model, the nice thing is that it will also do the prediction part besides giving you something that's understandable. So if the accuracy or the performance of that model you feel is good enough, then you can just use that rather than using a neural network or some other model.
Thank you. There's another question. Can we feed any model to AIX360, e.g. XGBoost or Random Forest? Also, how is it different from SHAP?
Right. So so you can feed in the sense, so this is an explanation toolkit. So I think SHAP is probably the most relevant method. So where SHAP lies is, so I showed that tree. So where it would lie is in the branch which says basically local explanations and post hoc. The way, so if someone adds SHAP, it would essentially fall under that part of the tree. The way CEM is different is that, for example, like Vijay just showed, it can tell you things like minimal changes, which will essentially change your decision, which SHAP does not. The other thing is that the pertinent positive part and the pertinent negative part, there is a 100% guarantee that the PP will lie in the original class and this pertinent negative will lie in a different class. With SHAP and Lime and other things, the explanations they provide are mostly based on correlations. So there's no guarantee that the new points that they highlight or the features that they highlight, if you just focus on those and say set everything else to 0, that you'll get the same class and so on and so forth. So in a certain sense, this is a more sort of causal way of explaining things. But in terms of the category of methods, it would lie in the same class that CM lies currently.
Thank you. There's kind of a follow-on from the original question. If you only base the rules on historical data, learning from best practices, what about unknown new behaviors next?
Right. So I mean, so if the so as the data updates, so as if you see that things are erroneous or that's not how you want things to, so there are ways in which you could update the model, but that's a general sort of machine learning question, in the sense that you might have trained something, but then the behavior or response to certain things might change over time. So how do you essentially update a model? So you would use similar strategies here. So it's that's I think a more sort of general kind of question.
Just to add a small point to that, so typically when you train the model, you're using historical data. But let's say the model is actually running on an instance, right? That model has not seen, but you want to explain that instance. So at that time, you could use any of the local explainability techniques. But since you have sort of learned the model on historical data, if you want to sort of investigate what rules has the model learned, then the data has to be historical. There's really no other option there to sort of understand the behavior. But you can use local explanations to understand the behavior of the model on how it behaves on unseen instances. Every new data point that is coming to predict the model, it will actually provide you explanation for that prediction.
Thank you, Amit. Thank you, Vijay. That was great. Please thank the speakers in the chat if you enjoyed the talk, and I'll be posting the recording shortly on the Csig page. And next week we have a report from a conference and a recent conference. And so that should be exciting. It'll be run as a panel, so do join us. Thank you.
Thanks, Suzanne, for having us, and thanks everyone for attending.
Thank you.
Thank you.
Thank you. You're getting lots of thank yous in the chat, so that's nice.
Thank you.
Thank
you.
And
please feel free to, send us follow-up questions.
Yeah, because if you want people to contribute or to help, it's great to connect.
Right, and And already people have started like posting questions on our GitHub in terms of issues. So I mean, yeah, everyone is welcome to. Yeah.
And we also have a Slack channel on the GitHub,
Right.
so please feel free to join the Slack channel and post questions.
Do you want to put the GitHub and the Slack or whatever links in the chat?
Sure, yeah.
Okay, yeah, I think I have to leave because I have a follow-up meeting.
Thank you. Thank you very much.
Thank you. Thanks a lot.